How many students am I expecting in class? Where is the course rep? Okay. So do this for me.
27.
27.
Yes,
So
please.
we have 27 in class. Are you 27 in all?
For now, the name that I'm having is 27.
No, I mean, how many are you in class? How many are you supposed to be in class?
50.
50, yes. So what you do for me is I'm checking attendance. So everybody send your name on the chat for me. Just chat your name, type your name and send it on the chat. Okay, I'll read it and then record my attendance. So do that while the class is going on. Now let's start. Very well, I hope you can see my screen. Yes, so today we're looking at functions and graphs, okay? And like I said in class, we want to, oh, okay, sorry. Because I'm meeting you for the first time, let me go through the course outline with you, okay? Very important. So I'm going to stop the slides for now and share the course outline with you. Okay. Um, okay, so basically we are here to look at the application of or let me say calculus, okay? When I talk about calculus, the main thing we'll be looking at in class is the concept of differentiation, its applications, integration, and applications, okay? But before that, we'll be looking at some pre-calculus topics like functions, indices, initial equations. We'll look at the series and sequences. Yes, some very basic topics, rational function, partial, okay, functions. Okay, these are some prior topics we'll be looking at. We will also look at limits of functions before getting to differentiation, okay, and so on and so forth. Now, at the end of the day, we are expecting to understand the concept of hyperbolic functions, which are part of trigonometry functions, okay, and know how they are used in our engineering applications. We're also supposed to understand the concept of calculus, like I said, okay, to be able to know the rules of differentiation and apply them. Okay, and prior to that, we'll have to also look at the concept of limits. Okay, and then once we
Okay.
are done with the laws of differentiation, we'll also look at the application, how are they applied. Then we move on to integration and the applications. And then as the third objective measure, we'll be looking at what complex numbers are, okay, and then look at some few applications on complex numbers as well. And then finally, we look at series and sequence, where we introduce ourselves to sequences like Maclaurin series. We'll look at the Taylor sequence and Taylor series, look at the Fourier series. Okay, that is where we'll wrap up our course. So as a weekly outline, I have these topics outlined like this, and I've already sent it to the course reps. So by now, this outline should be on your platform. Okay, so week one, we are supposed to look at functions, relations, and graphs, and then we'll continue from there. Okay, I wouldn't spend so much time on it because we don't want to exhaust the full 3 hours. Okay, online. We don't want to lengthen things. Okay, so I'm going to end on the first topic, which is on functions, relations, graphs, and graph of functions. Okay, where we'll be looking at the plots of various graphs, polynomial function, exponentials, logs, trigonometry functions, and other functions. Okay, good. Now, the key things we have to understand is when it comes to this particular course, we'll be using, okay, we have the reading text here. Okay, so you can get access to these reading materials, which will help you in your studies. Then again, as I wanted to mention earlier, you need to do an independent work. So once you are given assignment, ensure to do a sincere work. Okay, we do not want to encourage plagiarism. My own style of encouraging students to do a sincere job is to repeat about 30% of your or to bring about 30% of my exams question from your assignments. So which means that if you fail to do a sincere work when I give you assignments in exams, you are very likely to struggle. Okay, so make sure you do your assignment yourself. Even if you work in groups, make sure you understand, because it is very likely the questions you are presenting as solutions to me will show up in the exams, and you will struggle if you didn't do it yourself. Okay, so take note of that. The grading schemes too, eventually, I'm sure other lecturers have taken you through, so I wouldn't spend much time on that. Okay, so now another thing we have to know or need to understand is, because these are our first time in school and first year in school, there are a number of challenges that could come up, okay, which could easily distract your academic work. But as you've been oriented, if you have any issues, you can talk to your academic counselors. We have the HODs, we have the coordinators. Then you can even discuss things with your lecturer when you're having any problems. Okay, so that we see how best to assist you. Okay, in all areas. So if you have any issue, both academic, non-academic, you can talk to your HODs and to your academic counselors, okay, to assist you so we ensure that you are able to pass this coursework successfully. That is the focus and the interest of the university and even your lecturer, okay? The main focus is for you to pass the course successfully and transit to the next stage of your academia. Okay, so having said that, I'm going to end on the course outline and then take my attendance quickly. I have Gabriel Ama in class. I have Salisu Mubarak in class. I have Dennis Sai in class. Josephina Bekwe. I have Hariho Wushu Manahini, Kaiser Christopher, Millicent Mensa, Togbe Sylvester Yao, Befo Michael Kwabina. If you've just logged in, the instruction was to type your name and send it on the chat so that I can use that for my attendance. Lovely Benjamin Mensa, Dennis Sa, Ewa Collins, Emmanuel Rule, Ohini David, Tete Ketura, Sakpaku Andrews, Felix Osei, Sawuda Osman, Anefi Douglas, Daniel Wusu, Osei Gideon Asari, Abdul Malik Rashid, Salus, I think I've seen already. Okay, so these are the names I have for attendance today. Did I mention Christopher Kaiser? Christopher Kaiser, I'm not seeing you. You didn't send your name. Please take note. I'll use the names I've just mentioned. Okay, I've mentioned Christopher Kaiser already. Okay, that's fine. Yeah, so let's begin with our class. So we are looking at, and once again, those who have your videos on, please put it off. We don't need to see you, okay? We don't want to see you. So just put off your videos to make our bundle easier for us. Okay. Yeah, so let's continue. So functions and relations, and as well as graphs. What are we looking at in class today? We are basically going to look at, please, no hands up at this time. The issue is, if you didn't hear your name, type your name in the chat. That is the instruction. So don't distract us now. Okay, so what are we expecting to see? We want to look at the definition of functions. What do we mean by functions? Plot some graphs, explain the concept of domain and range of a function, and then use computer software. We are going to use a software to display the graph of functions. First, we'll look at it, how to plot it manually, and then how to use computer to generate the function, okay? Now, the whole idea behind using a computer software to generate the function is for us to, be excited, okay? Yeah, just to intimate us to further study, okay, or explore these functions at home. So you explore and then examine the behavior of the various function, okay, once you have the software on your own. Okay, so all these functions that we are looking at, we'll plot them, and then your work at home will be to explore it further and know the behavior of the function. Now, moving on. The first thing we need to understand is a function. I wish I could go to the... So a function is a relation, okay? It's a relation or a rule with the property that each input has exactly one output, okay? And the first thing that comes into mind when we talk about relation It's a link between two things. Okay, good. So when you go to Facebook, the first time you set up your account, by the time you finish setting up the account, okay, you have recommended friends, okay, for you. Then the question is, how did you know, how did the computer know that these are your recommended friends? It's because you stated a rule that probably you completed this school in this year. So what the computer will do is it will how do you call it, mine for all individuals who completed that institution in that year and present them as what, possible friends. Okay, because they were your classmates. So once they were your classmates, it's likely they are your friends. So a rule or a relation, okay, links one object to the other. Now in a function, what we are saying is we cannot have the rule linking one person to many people. It can only link one person to another person, just singular. Okay, and then in practicality, this is what it means. If you put tomatoes in a blender, the function on that is to blend to a puree, you are expecting a puree at the end of the day. So if you end up having let's say condo after blending, you'll be very surprised and amazed that what kind of blender is this? Okay, because it's not supposed to happen. So when such a thing happens, we call it an invalid function in mathematics. Good. Another practical example will be having a rocket which has been designed and programmed, okay, based on some functions and some rules to land in the moon. But this particular rocket, based on that function, could either land on the moon or on the sun. And if I ask you whether you want to be in this rocket or in this launch, you tell me no, because you are not sure whether you land on the sun and fry or you land on the moon. Okay, so functions need to have a rule that leads from one object to a unique image. It's very important. Now, the object which the function picks on, okay, and maps is usually referred to as the input or our X, and they are usually in a set called the domain. And the images of the X are referred to as the range or the values of Y. So practically, this is how it looks like. In the lower stages, we usually represent them like this. You have your domain X. I wish I could use, let's see. Okay, no problem. Let me use this screen. So you have your elements of the domain X, and then the elements of the codomain Y. Okay, good. So we take elements X within the domain, and then the function maps to elements Y. Okay, so F will map X to Y. This is what we mean. Okay, now moving on. I have a table on the right hand. We have elements in the domain and then elements in the range. Okay, and the assignment here is somebody's microphone is on. Okay, so mute all your microphones to avoid feedbacks. So when you look at the pattern here, we have 1:2, 2:4, 3:6. 4 will be to what? Yes, class. 4 will map to
8.
8. 10 will map to
8.
12.
10 will map to
12.
12.
somebody says 10 will map to 12. Is that true?
No, sir.
No.
No, sir.
20.
20. Then 11
Yes,
will
sir.
map to what?
22.
11 will map to,
22.
22.
and then 52 will map to
102. 104.
is it 104, right? Now the question is, how did
Yes.
we know that this will be the images of X? How do we know?
Because you multiply 2 by 2.
Because of the rule of the mapping.
Exactly. So what we are saying here is when the function picks on X, okay, it will multiply X by what? 2 to obtain the images Y. Okay,
Why?
so this is your X, and then this is your F of X, which is the image at hand. So F at 2. Sorry, this is F at what? At 3. Okay, so the function will pick on once X comes in here, which is the value 3. Okay, we get F of X or Y as what? As 6. That is what we do. Okay, so now you can mute your mic for me. Good. So we are saying that if that is the case, then Y is equals to what? 2X. And as we are aware, the functional notation is F maps X to an image Y. Okay, so if that is the case, then we can write F of X equals to Y. And if Y is equal to 2X, then we can equally write that F of X is also equal to what? It's equal to 2X. Okay, the same is exemplified on the left corner. We have Y is equals to X squared. F of X equals to Y, which means if Y is X squared, then F of X is equal to what? X squared. Okay, so the key thing we have to know from this slide is X is the input, and then our F of X or our Y, okay, is the output or the range, the images, which we refer to as the range. Okay, moving on. Now, when we come here, I think the rule is already written, but next I'll have to clean it first. So we have a rule. We are supposed to determine the rule between curing time in days and then block strength. That's the tensor strength. Okay. In the units is not stated though. So we have 1. 1 day is to 2. 2 is to 4. 3 is to 8. 4 is to 16, and 5 is to what? Yes. So 5 will map to what? Yes, class.
25.
25. Why is it 25?
5 raised to the power 2 give you 25.
No. If that is the case, then 1 raised to the power 2 should also give us what? 1 raised to the power 2 will give us what?
25.
Yeah, hello, Sarah.
You can multiply the 8 by 2.
I said that if you are saying it is squared, then 1 squared will give us what? Is it going to be 2? And is 3 squared also going to be 8?
No, sir.
That is not squared.
No. Oh, okay.
Say you multiply the 8 by 2.
8 by 2 instead. No,
8 by 2. No,
Yes, please.
we are looking at the rule from X to Y. That is what we are looking at.
Say
Yes.
the 2, the 1 was added by another 1.
So I think it's 32.
You think it's
I think 5
32,
maps
eh?
and 32. Yeah.
Say you add the curing time.
It's
Oh,
32.
So here, when you look at it carefully, okay, you realize that there is a pattern in your Y. If you want your
there's a
pattern,
pattern.
4 divided by 2 here. Okay, let me change my marker.
Yes.
So probably yellow to do. So 4 divided by 2 gives you 2. 8 divided by 4 gives you 2. 16 divided by 8 gives you 2. So which means that we are talking about a common ratio. Okay, common ratio in this pattern here. Okay, yeah, which suggests to us that we are dealing with a geometric progression, a GP. Okay, for those who know about AP and GP, you should know what I'm talking about. If you don't know about it, no problem. We'll be doing series and sequence. So we'll look at it later. Yeah, so which means that our R here is what? Is 2 in the sequence. And your first term is also what? 2. Okay? So if we put it into the general formula, which is UN is equals to AR raised to the power n minus 1. Your A is 2, so you put it there. And then your R is also 2. So you substitute into the formula. That will give you 2 into bracket 2 raised to the power n minus 1. But our n, the n is the input here, which is x. So we have 2 raised to the power x minus 1. So that is the general function. You may want to try it and see whether it's true. When x is 1, we are going to get 2 times what? 2 raised to the power 1 minus 1 will be 0. And then 2 raised to the power 0 is 1. Okay? So 2 times 1 is 2. If x is 2, we'll get 2 raised to the power 2 minus 1. 2 minus 1 will be the power of 1. So 2 times 2 raised to the power 1 will be 2 times 2, which will be 4. Okay? When x equals to 3, when x equals to 3, we'll have the power to be 3 minus 1, which is 2. So 2 raised to the power 2 will be 4 times 2 will be 8. When x equals to 4, 4 minus 1 will be 3 in the exponent. Let me write it properly. So in the exponent, we'll have 3. 2 raised to the power 3 will be 8 times 2 will be 16. So this is the rule that governs what? This particular observations, okay? And that function is generated as what? F of x is 2 times 2 raised to the power x minus 1. Now, let me draw your attention to this particular explanation, okay? Now, the data we have here, as you are seeing, is based on measurements from the lab. You understand? So this is what we have generated, let's say blocks, okay? We want to check the tensile strength of a block material. So we've mixed cement with water and aggregate, that's our sand. And then we want to check the tensile strength of the material, okay, for various days. So probably we have about 5 pieces of blocks. On the first day, we check the tensile strength of the material, then you record it. Second day, you check the tensile strength of the next material, you record it. Third day, you test the strength of the next material, you record it. 4th day, you check the strength and then you record it. Now the question will be, so on the 5th day, what do you think the strength of the material will be? And we are saying that before you even do the lab work, because you are noticing that the strength and the curing time are related by this function, you don't even need to go to the lab. Once you have this function, you can accurately predict what is going to happen, which is day 5. So 5 minus 1 will be 4. 2 raised to the power 4 will give us what? 2 raised to the power 4 will give us what?
16.
16 times 2 will give us what? 32. Okay, so mathematically you can determine the tensile strength even of your block before getting to the lab. Okay, that is the essence of this function. The functions help us to describe the patterns in data sets, okay, and help us to describe the relationship between two things. And when we talk about relationship, a typical example is the lab measurement. That is what we are talking about here. Any questions so far? Any questions?
No.
Okay. Okay, very well. So if there are no questions, I'd like to move on.
Sir, please. The one says is constant, right?
Yes.
Sir, please, the one constant.
That's the n minus 1.
Yes, please.
Yes.
The one, is it constant?
Yes, it's constant. It's a formula.
Oh, okay.
May I ask a question?
Raised to the power n minus 1. Okay. Let's move on. Okay, so what we are saying is, if we need to evaluate or find the image of a function given the value of the input, which is x, then all you do is to put in the value of x or substitute the value of x. Okay, so if x is giving us -3, then just put it into the function. By putting the function, this is how it will look like. So we have, you are just putting the values of x, okay, wherever you see x in the function. So you put it into x here. So we have 3 times minus x raised to the power 2 minus -3 in bracket plus 2. Okay, you see x itself is -3. So when you are putting it in, put it into brackets. Don't get confused and say there is already a negative here, so let me bring +3 here. No, there is a negative outside. So when you are substituting your -3, put it into brackets here. And again, when you are also squaring, put that into brackets and square it, okay, so that you don't make a mistake. Good. Then once you are done, you simplify it, okay. The same way, if x is giving us let's say a combination of terms or an algebraic expression, you need to follow the same rule. Substitute x wherever you see
M plus 3.
Yes. So you substitute your m plus 3 wherever you see x, okay? Good. And then what you get as a result is what we have here. So we're going to have m plus 3 squared minus m plus 3 plus 2, okay? Then you expand this one as m plus 3 times m plus 3, okay? Good. And then after that, you can multiply. That would be m times m will give us m squared. M times 3 should give us what? 3m. Then we have 3 times what? M should give us 3m. And then 3 times 3 should give us what? 9. Okay, good. And then simplify the ones in bracket to m times -1 will give you -m. 3 times -1 will give you -3 plus 2. okay? And then you group like terms and simplify to get this algebraic expression. Okay, so moving on.
Sir,
Yes.
please can you go over the f into bracket m plus 3 once again, please?
Yeah, the multiplication is m plus 3 squared is the same as when we say something squared, it means the same thing times itself. Okay, so it will be m plus 3 times m plus 3. So when you are multiplying, you either distribute this way or you can distribute that way. So m times m will give you m squared. M times 3 will give you 3m. Then 3 times m will give you 3m. 3 times 3 will give you 9. Okay. Then here to m times, this is when you see minus, it is minus 1. And there's 1 in front. So it is m times minus 1 will give you minus m. 3 times minus 1 will give you minus 3. Then you bring your plus 2 and then simplify it. Okay. When you simplify, this will give you what? Just group like terms and then simplify. That is what I'm saying. Okay.
Say thanks. Thank you.
You're welcome. Yes, Emmanuel. Emmanuel, speak.
Hello, sir. Please, sir. My question is, when you read the binomial expansion, please, sir, can you work it on like where you are doing the work, or you should work it on another sheet so that when you finish, you bring the answer?
No, I want to see the steps. So in any examination or any assignment I give you, make sure you indicate the steps. I'm not interested in the answer. I'm interested in the process and the answer. So if, yes, if you skip the steps and give me the answer, you lose a lot of mark. Yes, Katira. Katira, you have your hand up. Katira Tete.
Sir.
Yes.
Yeah. What? I didn't really get that side.
Katira, your line was breaking. Can you come back? Okay, if you're having difficulty, just type your question in the chat for me. Okay, let's move on. So the next thing we want to understand is the concept of domain and the concept of the range. Now, when we talk about the domain, first of all, you have to know they are the values of X. They contain the input values. So you remember when we do the first charts, we said the domain is the values of X here, and the codomain is the values of Y. Now, when we come on the graphical representation, this is the X-axis. So the X-axis contains the values of X. And then the Y-axis contains what? The values of what? Of Y. So when it comes to the graphical display, if we want to determine the domain of a function, it will be the values of X for which you can see or where you can find the graph. Okay, let me put it that way. So the values of X over the graph, let me put it that way. So you have the graph spread over -4 to +2 here. So within this interval of X, you can locate our graph. That's what I'm saying. So within the interval -4 to 2, we can locate this graph. Outside negative, outside -4, when you go here, you will not find a graph. The same way to when you go beyond +2, you will not locate this graph. So we say that the function exists over this given domain or this range of values, -4 to 2. Okay. Now, another thing we have to take note of is, you first, let me write it. So we are looking at the interval -4 to 2. When I bring comma, it means we are starting from -4 all the way to 2. Now, another thing we have to note is when the graph, the edge of the graph has been shaded. Please, those with your microphones off, mute it. So when the end of the graph has been shaded, it means that that particular value of x is included. Okay, so when it's shaded like this, we make use of the square brackets. It means it is closed or it is part of the domain. And then the same way, because the side 2 is also shaded, 2 is also part of the domain. So you close it with a square bracket. If it was open like that, if the edge was open, you open the brackets. If the edges were open round without being shaded, you have to just open it. It means that that particular point is not part of what? The domain, or it's not part of the interval we are considering. Good. Now that we have understood this one, we also need to write it in the search notation. I want to connect it to previous knowledge. Okay. So in the search notation, we would have written this information as what? X is such that X belongs to real numbers and X lies between, that is the domain. The element X, the elements in the domain are between -4 and -2 inclusive. Okay, that is less than or equal to 4 negative, and then sorry, X is greater than or equal to -4, and then less than or equal to +2. Okay, that is how it would have been written in the what? In the set notation. Sometimes too, in expression, we may just write it as a X, okay, it's in between what is less than or equal to, greater than or equal to -4, and then less than or equal to what? +2. We could just write it this way. When you see it like this, it's the same as what we've written here in the set notation, and it's the same as what we've written as in the interval notation form. So that is how you get to define what? The domain of a function. Any questions? Okay, then let's go to the range of a function. Now, with regards to the range of a function, like I said, the range of a function is defined by elements of y. Okay, so those set of values are on the y-axis. So if you are looking for the range, it is the values of the function or the possible values of y where we locate what? The function. Let me put it in that way. Okay, so the set of images y, okay, on which we have our graph, the lowest point to the highest point. Very good. So when we come here, we can see that the function is in between -4 and +4 here. So for our range, we have -4 all the way to +4. So the graph is spread from -4 to +4 on the y-axis. And then because it is shaded, we have to what? Close the interval. Okay. So in other words, our range is such that y is less than or equal to +4, but greater than or equal to what? -4. That should be our range. Okay, so the range is the set of values y, okay, for which the function is what is graphed or is defined. Okay, having said that, let's move on. We've understood the concept of range and domain. So the next step will be to plot the function itself. How do we plot the function? So let's clear the screen and look at how to plot the function. Yeah, so before then, there are further examples. So when you look here, okay, once again, this is the function here. This is the graph of the function, and it starts from 1 here. It starts from 1, but it keeps going. The function keeps going. It is not ended. You can see an arrow. So the function is going all the way to wherever it will stop. Okay. So we say that the function is defined over the values of x greater than or equal to 1. That is what we have here. That's the domain. And then when it comes to y starts from where 2 upward. It is going up. We don't know where it will end. So we say that y is greater than or equal to what? 2. In this concept, in the next example, we can see that x ranges from where? From -2 here to +2. So we say that x is in between what? -2 and +2 inclusive. Okay. Whilst y is also in between 0. Y is 0 here, and then y is 3 here. So we say that y is in between 0 and 3 inclusive. Okay. So let's move on. We want to plot some graphs. The first graph we want to plot will be the function, this function. So you can just take note of it, 2x squared minus 2. And then the domain of x is in between -4 and then +2. So I'm going to log off the screen. You can take note of the function, 2x squared minus 2, and then x between -4 and 2. Okay, good. Take note of it. I'm going to log out the screen. Then I go to the software we'll be using to plot the graph. So on my screen, I have the Scilab 6.1.1 console, okay, which is very similar to MATLAB, very portable version, okay, and the language is C++. So if you have an idea of C++, that will even help. Now, like we said, our domain of the function x, okay, is equal to -4, okay, all the way to +2. So I have -4 is to +2. Please, can you see the console Scilab?
Yes, sir.
Good. So I've defined the range. Look at the interval of values it's giving me: -4, -3, -2, -1, 0, 1, 2. Okay, good. Now my function is my y sorry, f of x is defined as either f of x or y, because we know f of x is equals to y. Okay, so let's make it y is equals to, we were told 2x squared, so 2 times is multiplication is star, so 2 times x raised to the power 2 minus 2. Okay, that is the function we had. So once we type this and then enter, we have the values computed for us. Okay, so we want to plot our points and then see the graph of the function. You are going to use a plot command. So we plot x comma y. If you are not asking a question, just mute your microphone for us. We do not want to hear. Okay, we have plot x and y. Once you press on enter, the command is initiated and the graph will show very soon. So that should give us it's taking a while, but it will come. Yeah, so this is the function of the point. You can see we have our point here. We have another point there. You have another point here. We have one point there. We have a point here. Okay, and then the final point there. So these are the points we just plotted. -4 as against 30. Okay, that is it. -4 and 30. -3 and 16. -2 and 6. -1 and 0. Okay, so you select, let's say -1 and 0. You come and locate -1. Then you gauge all the way to 0, which is on the y. Then you plot your point. Okay, the same with 0 and -2. Locate 0 on the x-axis. This is the x-axis. So you locate 0, this is 0. And then you are plotting 0 and -2. So this will be -2 here, -2. So you locate the point all the way, and then you go and plot that point. The same way 1 and 0. So this is 1, this is 0. So you plot your 1 and 0 point here. Okay. And then finally we have 2 and what? So the last point is yeah, so our last point will be 2 and 6. Okay, so you locate that point 2 and then you plot it. Now this is how we can generate the plot of our function. Now by plotting this function, the most important thing I need you to understand is, you see, it tells us very much about this function. The first thing is, we know the domain of the function starts from where? -4 to 2. These are your x values, the domain. Okay, so this is the domain of the function. And then we also know the range of the function. The range starts from here all the way to the top over here. So this is our range of values. Then another thing we know is this curve seems to, you see, the curve is decreasing. You can see that the value of the function was decreasing whilst we were going until we get to a minimum point here. So there is a decreasing value of the function.
Yes, sir.
The function was decreasing till we get to a certain point, then it begins to what? To increase. Okay, so here we are increasing. And such a point is first of all called a turning point. Turning point because it has changed, okay, the state of the graph. It's changed it from a decreasing state toward an increasing state. So it's a turning point. Okay, so we call it a turning point, usually represented as TP. But what type of turning point is this? Clearly, we can see that this point is down, down, down. So we call it a minimum turning point. So for a minimum turning point, the graph will always come in decreasing, but after that minimum turning point, it will start increasing. So every minimum turning point, in every minimum turning point, while the graph is coming in, okay, or x increases, okay, when the graph comes in decreasing, it will end up what? Increasing after the minimum what? Turning point. So we call it a minimum turning point. Yeah, so this is quite interesting. We want to plot the same graph, okay? But this time around, or let's change it. Let's change it. The graph we've just plotted is a quadratic graph or a polynomial function, which is a function, say f of x, which is equal to 2x raised to the power of 2 minus 2, given the domain. So this is quadratic, which is a polynomial function. Now let's take another polynomial function. Let's say f of x. We want to see the turning point properly and understand some other properties of what? Of graphs. So let's take f of x is, let's say, minus 3x raised to the power 4, okay, plus 2x cubed minus, let's say, x, okay, x plus 2, okay, good. So this is also a polynomial of degree 4. The degree is the highest power in the function, okay, so for x. So this is the degree. In this case, the degree is what? 4. The same way to this is the degree of the polynomial function. I'll show that to you. But since we are considering it, I'm just touching on that. So this is also the degree here. Here the degree is 2. That's the highest power in the equation. Okay. So I'm going to let's define the domain of x starting from, let's say, -3 to say 4, 4, and then that will be inclusive. So that will be our domain. So I'm going to graph it again. Let me clear portions of the Please mute your mics if you are not using them. Just mute it. Ernest, mute your mic if you are not using it.
Yes, sir.
Okay. So we'll define our x, which is our domain. Okay, starting from negative. Before we do this, I want you to know, instead of going like this, in the first case, the intervals were 1, 1, 1, 1. But if I want a very smooth graph, I can change the intervals and then rather make it 4. 4 is to half, meaning the intervals will be smaller. Instead of using 1 as an interval, I'd rather use half. So 1 is to half is to 1. And I'm going to do same here. So this time I'm going to type x equals to minus 3 is to, I want an interval, a smaller interval. So half is to 4. Let's see the output generated. You can see it. So instead of moving from -3 to 2, -2, -1, 0, 1, 2, 3, 4, you see it's halved the interval for me. So from 3 to 2.5 to 2 to 1.5 to 1 to half to 0 to half, 1, 1.5, 2, 2.5, 3, 3.5, 4. Okay, so I've halved the interval. Now let me also type my function. So I have f of x, or let me say y, is what? -3 times what? X raised to the power what? 4 plus 2 times x raised to the power what? 3 minus what? X plus 2. Okay, good. So once I type it, it will give me the range of values of y. That is it. It's computed the values of y. Then I want to plot the function. So I'm going to use the same command. Let me clean this side. So let me use plot. So plot x, comma y. Okay, and then once we plot that, the graph will show. So this is the graph of the function. Okay, as we can see. Now I want to change. I want to see the behavior of the function properly. So I'll change the interval. Let's change the interval. We want to see it on a very larger interval. So let's say we are choosing an interval from -10 to +10. Okay, so let's change the interval. I'm going to change it from -10. Then this time I'll use 1/4. 1/4. That's 1/4 is to +10. Then I'm going to have the same function again. So y is this, and then I'm going to plot x and y. So let's see the display now. We have a smoother graph. Okay, it looks like a parabola, kind of getting constant along this line here. Okay, that is the kind of function we are having. It's still not very clear. We are supposed to have 3 turning points, but the graph is not really displaying it as we expect to see. Okay, but certainly that is the graph of, if we extend the interval, we want to see it clearly. Let's say if we pick from say -20 to +20, let's see what will happen. I want us to see the true picture of the curve. So let me use 30 this time. 30 is to 1/4. Okay, is to 30. I'll mute the expression. Then I have plot xy. Okay, so certainly this is the nature of the graph. It's supposed to show the pattern somewhere here, the turning here, but we are really not seeing it. We are not seeing it, but that is the display of this particular graph. If we set the set of points, we are going to get the function as we see here. Now let's try another graph. Let's say this time we want to go, let me go to my slide and see if we can get a very nice function. I want to plot, let's get a polynomial function. let's say, yeah, so we have a function like this one, x cube, let's have the function x cube, or x cube minus 3x. So I want to use an interval, say this, and then plot the function x cube. I want to plot the function x cube, 3x cube minus, let's say, we just saw 3x cube minus minus 3x. Okay, so 3x cube minus 3 times x. Okay, cool. Then let's plot. Before you plot, you have to close the previous graph, else it will plot on the previous graph. So when we plot, yeah, beautiful. So we are seeing a very nice graph. Okay, it's giving us a different picture entirely. So here, this graph is very important for us. We are seeing that the graph we just looked at is x cubed minus what? 3x, okay, minus 3x, which is, that's the function f of x is equal to x cubed minus 3x, okay? Now, for a polynomial function, you always have a number of turning points which is equal to the degree minus 1. So if the degree here is 3, then the number of turning points of the function should be 3 minus 1, which is 2. And clearly we are seeing 2 turning points. When we come here, okay, it keeps coming down. The function is coming down and coming down and coming down. Then when we get to a point, okay, the function appears, it's not too clear, but it's a bit up. It's not too clear, but it's here, it appears to be stationary. But if we are plotted over a shorter range, we would have had, maybe we'll plot it over a shorter range for you to see. So there will be one turning point here, and then we have another turning point here. Whilst it's coming up, okay, at a point it drops and then begins to go down again. So there is another turning point here. So we have 2 turning points. This will be the minimum turning point, the main turning point, and then this will be the maximum turning point. Okay, then again, what we need to understand is, because this is the minimum turning point, okay, I think I've explained that already. Because it's minimum turning, we've already said for minimum turning point, you come in decreasing, but you leave what? Increasing. And for maximum turning point, you come in increasing, but you rather leave what? Decreasing. That is the unique thing about turning point. So we have the minima and then the maxima over the given word domain. Now, the next thing I want to talk about will be on, we'll come back to the properties of the functions, okay? But, okay, fine. Let's look at other type of graphs, other type of functions. Then we know we are done with all the functions in terms of their graphical, okay, representations. So we want to look at a function like the logarithmic function, okay? So when we talk about log functions, they look like that. I'll go to the slides, we will look at it from the slides anyway. So log functions are of the form, maybe 2 log of what? Log of x. These are logarithmic functions. So we can also have exponential functions. Exponential functions go this way. Okay, so we can have, say, a base raised to the power an x, okay, or more generally a certain base raised to the power of what? X. A common example of an exponential function is e raised to the power x, which is the Euler's number. We'll look at that in the slide. So all of these are different functions. Then we also have what we call as the trig functions. The trig functions to come in their own forms. We have f of x, which is equals to cos of x. We have cos function. Okay, we can also have the sine function sine x. Okay, we can have tan x. We can have cot x. Okay, then we can have the hyperbolic functions to which are the cos x, the sin x. We have the sin x. We have the tan x. Okay, we'll be looking at their relationships, okay, later in class. All of these functions are there. Then we have the cosec, the cosine. We have so many of them, okay?
Yo.
So,
Okay.
what we want to do now is to just demonstrate how to plot them so that at home you can continue, okay, with the plots and examine how all these functions go. So let's try for the first one, which will be the logarithm function. So for the logarithm function, the domain should always be greater than what? 1, okay, or greater than or equal to 1. So we can choose x greater than or equal to 1 to the value, let's say x in between 20, okay, and then see how it will work. So let's plot that. We have x is 1 is to 20. So this time I'll half it. X is to 1 is to half is to 20. I want to suppress the data. Then the next one will be f, or y is 2 times what? Log what? Log of x. Okay, good. I'll suppress the output too, and then plot. We're going to plot x and what? And y. Okay. So clearly we are seeing the graph of this function here, which we just created. That's the function we just graph. F of x is equal to that. So that gives us the nature of this graph here. Okay, good. Okay. Now, if we come to the exponential functions too, we can equally graph them just by raising the value of x to that power. Let me demonstrate one for the cos function. So for the cos function, let's demonstrate that. I want you to be able to plot all of these at home. So cos function, let's start from negative 360 to, let me use let's say half, or even 1 is okay. 360 to 360. I'll suppress the image. Then we want to y to be equal to, let's say, cos d of x. Okay, we keep the output. Then I want to plot x, y. Like I said, always make sure your previous graph is closed before you graph. So once we plot it, Yeah, we are seeing what the graph of the function cos of x, okay? Yeah, and then clearly we can see that given the domain, which is from negative, when you look at it, from negative what? I stated negative 300 toward positive 300 here. And then you realize that regardless of the value we give, y is always in between -1 and 1. So the range of the cos function or trig functions, the cos and sine functions, as we are seeing, is always in between what? -1 is less than or equal to y, is less than or equal to what? To 1, +1. So the function is always in between what? -1 and +1 for the range of values. Okay. Any questions on the plots we've done so far? Any questions? Okay, if there are no questions,
Yes, please, I have a question.
go ahead.
Yeah, my problem is that the network was going on and off, so I can't really catch up very well with the graphing area. Yes, so I find it difficult to understand along the line.
Yeah, that's not a problem. That's why we're recording it. So
Okay.
we record because of network issues.
Okay.
Yeah, so that can be addressed later. You just have to get a video and watch
Okay,
it
sir.
and follow. Yes. Okay.
Okay.
Fine.
Thank you, sir.
Yes. So having said this, the graphs have helped us to summarize, okay, everything we wanted to talk about in class. So we know that at a point in time, graphs can increase and decrease. And then where they increase and decrease is a maximum turning point. And then when we are decreasing and we begin to increase, we have a minimum turning point. We also know that for polynomials, let me scroll down all the way to the polynomial function. Okay, so for the polynomials, we have this for the slides. I think I've already sent it on the course reps page, so that will also is also available to you. So when you have a polynomial with degree of 1, first of all, let's look at the general polynomial. I think yes, this is the general polynomial function. Okay, f of x is equals to an x raised to the power n plus an minus 1 s raised to the power n minus 1 plus dot 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 plus your constant. Okay, good. So the highest power of x gives you the degree, and x, the degree should always be a positive integer. That is what we have to note. Okay, so for examples, when you come here, a function like 2x raised to the power 4 minus x, the degree is 4 and it's an integer, so it's a polynomial with degree of 4. Okay, when we come here, 2x raised to the power 0, polynomial with degree of 0. 2x, 2 times square root of x. Square root of x is the same as 1 over 2. Now, because the power is not an integer, it's 1 over 2, rational number. Okay, so it's not an integer. So this cannot be a polynomial. The same way, raised to the power 3 over x is x raised to the power minus 1. This is also a negative word integer. Okay, so this can also not be what a polynomial function. Now, in summary, we're saying that the degree, the highest power of x is the degree. Okay, so these are the various names given to it. When the degree is 1, we say it's a linear function. When degree is 2, we say it's quadratic. 1 degree is 3, we say it's cubic. 1 degree is 4, we say it's quartic. Okay, good. And again, what we need to understand is the degree determines the number of turning points. So in a linear function, the degree is 1. So 1 minus 1 will give us 0 turning points. That is why there's no turning point in the linear function. Okay. Then here again, the degree quadratic is degree of 2. So 2 minus 1 will give us 1. So that is 1 turning point here. Then for a cubic function, the degree is 3. So 3 minus 1 is 2. So you have 2 turning points, as you can see here. Then finally, we have a quartic function. For a quartic function, you will have 4, the degree of 4. So minus 1 will give us 3. So we have 1 turning point here, the second turning point there, and the final turning point down here. Okay. So in summary, the degree will determine the number of what turning point of the function. Now moving on, we have exponential functions like we've seen. That's the general form. I've already mentioned that. Then we also have the yes, the most important thing about this exponential function, which I would like you to learn now before you come to class tomorrow. Okay, just after class, I've made available the slide, so make sure you study it. Because exponential functions are just like indices, they follow the rules of indices. Okay, so we have the properties of exponent. When you have a base raised to the power x times the same base raised to the power a, you take one of the base and add the exponents. Okay, so these are the rules, and based on these rules too, I have examples. Okay, examples on the same rules that I've just talked about. So I'll need you to go through them, know the rules before coming to class. Please go through the notes today before coming to class tomorrow morning. Class will start at 8 o'clock. So make sure you go through the notes, okay, before coming in to class. Okay, so look at all the rules and the examples I've given you. Okay, and then when we come to class, we'll continue from there. We've seen the plot of exponential functions already. That's the Euler's number. Okay, then finally we have the graphs for trig functions too. I think we've seen the plots for the cos function. Is the same for the sine function, and so on and so forth. Okay, then finally, before we wrap up, I want to touch on the concept of piecewise functions. So when we talk about piecewise functions, where is yeah, this is an aspect we didn't look at when we were doing the graph, the relative minima and the relative maxima. Now, when we say maxima, we mean they are the maximum points, just like the maximum turning points. Okay, so here in maximum turning point, you come in increasing and then you leave decreasing. The same way here, come in increasing, you leave decreasing. In a minima, you come in what? Decreasing, and then you leave increasing. Now, the reason why we don't refer to this as maximum, absolute maximum and absolute minimum is the domain of this function has not been defined. What I mean by the domain has not been defined is this function can keep going. So maybe in the next values of x, it might be like this. Okay, so we can have another what maxima here, which can be bigger than the maxima here. So we cannot conclude, as long as this domain has not been provided, we cannot conclude that this is the absolute maximum value. So we say that it's a local maximum or a relative maxima. In the same way, because the domain has not been defined, we also say that this is a relative what? Minima. They are relative because in comparison to others outside the plane, these are minimum points, but we cannot say they are absolute until the domain has been what defined for us. Then finally, I'll look at the concept of stepwise function. So this is a stepwise function. What we mean by a stepwise function is, I'll just demonstrate with, there's supposed to be, okay, I had special, no problem. Let's use this one. Okay, so what we mean by a piecewise defined function is a function, I mean, definition is different on every given domain. So let's say if I give you the value x is equal to 3, you first of all have to come to this function and then come and look at the two domains. Which one satisfy, these are the domain. So which of these two domains satisfies the x equals to 3? So x equals to 3, when we compare these two domains, here we are saying x should be less than or equal to 1. So it is not this one. Then here we are saying that x is equal to 3. So x equals to 3 is greater than 1. So it falls within this domain. If it falls within this domain, then this is the definition of the function. So for x equals to 3, the function will be defined as negative x plus 4. Okay, good. Assuming I give you the value x equals to negative 2, you first come and compare. So negative 2, where does it fall? X less than or equal to 1. Indeed, it falls here. Okay, these values are greater than 1, so it cannot be here. So if it falls here, then the definition of the function will be f of x is equals to, that is the upper definition, which is 2x plus what? Plus 3. Okay, now where is this thing applied? Sometimes you may define a robot. In robotics, we may define different functions for the robot. So when there is a robot coming and there is an obstacle, we have this robot here on its way. And then whilst it is coming within the domain of, this is, let's say, 5 meters, okay? So whilst it is approaching 5 meters, where x is less than or equal to 5 meters, it is moving in a straight line, okay, with the function 2x plus 1. So it is coming with a straight line. So I'll say that the function is 2x plus 1. You let me just put it here like this, okay? But once it picks a signal that there is an obstacle, then the next thing to do is it will switch to another function, which is, you see, it's moving in a straight line. So to dodge this obstacle, it can move in a curvilinear path, a quadratic, using a quadratic equation like this. We've seen functions like this today, okay? So it can switch when x is what? Equal to 5 meters, or let's say greater than 5 meters. Then the function is now going to take the form of, let's say, 2x squared, okay, minus 1, okay? So here it is 2x plus 1 as against 2x minus 1. So what we are saying is, as long as we are coming and we've not met what this obstacle, where x is less than or equal to 5 meters, the robot is going to walk in a straight line. Straight line means you are using a linear equation. But the moment it picks what a signal of an obstacle and it gets to that 5 meters, it has to switch. It has to stop moving with a straight line and then begin to move with what? The quadratic equation, which will help it to go around the obstacle. Then probably after the obstacle, it will switch to another linear function to help it move in a straight line. These are some of the applications of piecewise functions. So we can see a graph of the piecewise function as defined here, okay, graphed or at this point. Okay, so on that note, I think I'll bring today's class to a close. Let me see if you have one or two questions. If you do, then I'll address them before we leave class. So let me take your questions before we wrap up for today's class.
Hello, sir.
Yes, I'm listening.
Sir, it's like, concerning about the graph, it seems like I didn't understand. So maybe, I don't know how you go and go about it. As you said, you have to.
Yeah, so the video is available if you came in late or your network was having a problem. The video will be made available to you. Just watch it. Yeah. Next question. Yes, Andrews. Please, if you have not asked a question, put off your mic. Andrews. Andrews, we only hear you.
Hello. Yeah, I'm asking whether if there is any handout for this.
Whether you have a handout.
Hello, sir.
Yes.
Yeah, I'm asking, is there any handout for this section?
No, I'm not a handout type of lecturer, okay? All my materials will be made available to you. I've already sent you the slide, and I will send you the video in due course too. Good, next question.
Okay.
Hello, sir.
Yes.
Sir, please, can you give us the objectives again? Because there is no hangout, so that we can.
The course outline has been made available to you. So look at the course outline. It will even indicate whatever topic we are treating every week. So course rep, you are supposed to have sent them the course outline and the slide by now. Please do that immediately after the class. Next question.
Sir, please, they've done that.
Okay. Next question. Okay. If there are no additional questions, I think some people came in. If you came in late, type your name so that I can take record that you were in class. Okay, so the next set of people I have in class, I have, I think I've mentioned these people's name already. Let's see. Usu Daniel, Douglas Anefi, Osai Gideon Asare, Abdul Malik Rashid, Yangsin Wilfred, Sadiq Abraham, College Kwanzaa, Ati Chogbu Linda, and Christian Kofi. So these are the attendance for today. Yeah, on that note, we'll end today's class.
Sir.
See you all
Sir,
tomorrow.
please, I have typed my name, but
Sir.
so you haven't mentioned my name.
Ernest Tine. Okay, so I've taken note of that.
Yes, please.
Sir,
Okay, sir.
sir,
Yes,
hello, sir.
Yes, who is it?
Sir, please, this is Alexander. I have typed my name, but so you haven't mentioned my name.
So I mentioned all names earlier. When did you type your name?
Sir, the time you tell us that you should type now, but I didn't hear my name.
Yeah, so I've already mentioned your name if it was typed. So Alexander Isaac Osai. Okay,
Please, yes.
noted. Yeah, so
Okay, thank you, sir.
we'll end our class for today. See you tomorrow, God willing. Bye-bye.
Bye.
I can't see anything one over. Hey, maybe it's iPhone now.